statistics kind of guy per se, but I always found the idea of how it relates to your data interesting. It's like general relativity. I wouldn't want to study it, but I find it fascinating. Okay, so now any other example or any other geometry for calculating capacitance, basically you've got the same situation. The question is do you have a set or a pair of conductors that are arranged in a way that you can calculate an electric field and a potential difference relationship? If you don't, then you better just rely on directly measuring it anyway, because there's no way to calculate. But when you have, like, the associated line of charge, plate, flat, ring of charge, any of these surfaces like that, then you have the advantage of using this analytical approach to calculating and solving for a capacitance. But again, it really comes down to the skill set of solving for V. If you can solve for V, then you can solve for C. Can't? Then all bets are off. So a sphere, otherwise, you just concentric spheres, you deal with them the same way. Now, here's an interesting example. One of the things I wanted to point out by a physical example, especially when you have a measurement subject or a sample that is too small to physically measure with any reliability, especially if you're studying the electrical properties of this type of a system, we can note two things. First of all, for most biological membranes, for cell membrane lipid, which is the fatty acids, are the fatty acids that compose 99.9% of all of the structural substance of any cell. I believe the dielectric constant is right around 3. You can use measurement of capacitance to identify the geometry of a cellular membrane system, one that's too small to physically measure without destroying it, like a nerve cell or a cardiac cell, a myocyte. It's a very cool idea. This was a little bit of what I studied when I was in graduate school. I needed to know certain aspects of how proteins or of membranes that I was working with, or membrane systems that I was working with. Now, there's a couple examples of this that are if you had a relatively spherical cell, kidney cell, most cells other than muscle cells, muscle fibers, or axons, nerve cells, motor neurons, for instance. And this is kind of a cool thing, actually. It turns out that I left one thing out here. The thickness between the two surfaces of a biological cell is about 50 angstroms. So the cell thickness is about 50 times 10 to the negative 10th meters. Okay, this is cell thickness. Cell wall. Biologists would say, oh, it didn't have a cell wall, it's a eukaryote. Well, it's a cell wall. Now, what is it that this what is it that this cellular membrane separates? It separates conducting liquid, salt solution, on either side. So you effectively have a concentric spherical capacitor. So you can think of this as being a capacitor with a thickness, delta R, if you will, of 5 times 10 to the negative 9th meters. Only it's a sphere.
It's just positive on both sides.
Why do we lose our power of magnitude there?
Because I moved the decimal place.
Oh.
So now here's the thing. Cells typically have a certain voltage or cell membrane potential, we call it, across them. And it has to do with the leakage of a small amount of potassium from one side to the other. So you get an ion imbalance just along the surface of the cell. And typically, it's more negative on the inside than it is positive. And the voltage is typically, I think I'm saying typically a lot here, somewhere around 70 or 80 millivolts.
So it's just more negative on the inside, or
It's
it's
more negative on the inside because a little bit of these positive ions leach outside. And as long as it's held tight, the negative ions can't come out with them.
instead of sodium or
Potassium. It's potassium. Well, those are the biological details that I'm suspecting you're probably not so concerned with, but you've got a voltage across this thing. It's interesting though. It's very interesting because it's just physics. Again, we want to segment and separate all these ideas, and damn it, they're not. They're not different. They're the same thing. Now, the cell will have a certain radius. Let's call it R cell. And the radius of the cell is approximately equal to R1, which is approximately equal to R2. Now, R1 minus R2 is this value. Okay? So it's not that it's insignificant. You got to be careful rounding, certainly. But delta R, as I should have called it, big R, is R2 minus R1. So it's functional value. So if you could measure the capacitance of this thing, and you knew what the membrane potential is, you could in fact estimate the charge on either side of this cell. Well, estimate the dimensions if you knew the capacitance ahead of time. Or if you measured the capacitance, you could use that to estimate the amount of charge, plus and minus, on either side of this charged capacitor, and simultaneously estimate the quantity of individual electrolytes that would have had to have migrated from one side to the other in order to charge that thing. So it's very cool how this can be applied. Now, here's the thing about this. For cells, they're spherical. There's a whole section on spherical cells. Or I'm sorry, spherical capacitors in chapter 25. But because this value is so small relative to the dimensions of the cell, the cell thickness, this is like a parallel plate capacitor. Capacitance of a cell is pretty doggone close to the capacitance of a parallel plate capacitor. Which we can describe in terms of epsilon, the surface area of the cell, divided by the separation distance of the plates, which is delta R. I don't want to derive a spherical capacitor It's the same process, I don't want to waste my time with it right now. But it reduces to this because of the relative thickness of this thing in the whole. This for 50 nanometers. I'm sorry, 50 angstroms, 5 nanometers. And this is 3 times epsilon naught. If this cell had an area, if hypothetically, if our cell had a value of 1 times 10 to the negative 6 meters, typical cellular size. One of the funny things about our use of metric prefixes, micrometers are typically the size of cellular geometries, 10 to the negative 6. Nanometers, well, they're similar to the wavelengths of light. They're not 2 orders of magnitude. But they're also dimensionally similar to molecules, 10 to the negative 9. And then we use 10 to the negative 10 because atomic dimensions for individual atoms are typically around 10 to the negative 10 meters in size. So a lot of the reason why you see certain powers of 10 is 3 orders of magnitude, micro, nano, and even pico if we wanted to look at smaller structures still. There's a certain rationale aside for grouping them in thousands. Now, so what would the capacitance of a cell like this be? It's a 1 micrometer radius cell, and the difference between the inner and the outer surface is 50 or 5 nanometers. And this has a liquid dielectric constant. It's a dielectric of 3. What would this correspond to for a cellular capacity?
What's the difference between times 10 to the negative 9?
Yeah, 5 times 10 to the negative 9 is 50 times 10 to the negative 10. And I always think about it in terms of 50 because liquid molecules are typically chains of 20, 25 atoms. If you put them back to back, it's about 50 atoms. So when I think, and each atom has a dimension of about an angstrom. So when I think about it, I think of 50 atoms strung out next to each other, and each is a 10 to the negative 10th meter in radius. So that's just, it's my little pea brain thing.
So the capacitance of that is 6.67 times 10 to the negative 14.
That's what I've got.
Which would be 14 femtofarads. So 6 points, or not 14, I'm sorry, 6.67. So this would be about 6.7 times 10 to the negative 14th farads.
Femto is to the negative 15.
Yeah. 67 times 10,
Oh,
67 femtofarads. Yes, it's 10 to the negative 15. So let's just think about this for a second. How many equivalent electron charges would have to be on the surface of this thing to maintain an 80 millivolt potential difference with a capacitance of 67 femtofarads? What's the net charge on either face of the cell, and how many unit E's would that represent? It's not really electrons in cellular systems like this. It's physically ionized metal ions, but we can treat it this way. I want you to see it's more than just an esoteric. Just to give you another sense, what is the charge be? What is the number of E's per unit area of this cell? Steve would say, pretty easy. Q total, C times V.
Times B.
So we got 6.67 times 80.
And then-
So there's 5,500 times 10 to the negative 15th, 14th, 13th.
Yeah, I got 5.34 times 10 to the negative 15.
Yeah, that's what I got.
5 point what?
3.4.
Okay, so that many coulombs? How many unit quanta of charge would that represent?
That divided by 1.602 times
10,000?
19.
30,000.
10,000 ballpark. So the number of E
Yeah.
would be Q total, divided by E, and it's about 30,000. 33, 32, 31.
33,000.
Okay, so you got about 33,000. The surface area of this cell, you've already calculated that at some point. What is the area of this cell? Pi r squared. Doesn't matter which side face you use, there's not going to be a difference between the inside and the outside because the thickness is so
4
small.
pi r squared.
I'm sorry, 4 pi r squared. It's 1 times 10 to the negative 6.
No,
10 to the
0
negative
would be
12,
negative 6.
10 to the negative 11.
2.65 times 10 to the negative.
It should be times 10 to the 15th. 2.65 times 10 to the 15th.
Oh, when you calculate E per.
Yeah.
So the density of E over A would be 3.3 times 10 to the third, divided by a surface area that's about 10 to the 11, 10 to the 12, negative 12, 10 to the negative 11. You're not going to give me any of the individual values, so crap it. Just what's the number come out to be? Hopefully. you got-
2.65 times 10 to the 15th.
I got 10 to the negative. Oh, I did square it, that's why. Yeah, you're right.
So there's about 10 to the negative, or 10 to the 15th unit charges per meter squared. Of course, there's very few meters here, which corresponds to about 33, or 3,000, or was it 33,000? Did I leave out?
33,000.
33, it's 4, sorry. I'm just saying my words because that didn't make any damn sense. So when you think about molecular quantities, we typically think mole quantities, right? 10 to the 23rd, 10 to the 22nd, 10 to the 20th. The amount of little potassium ions that will flow from one side to the other, they all have a charge of plus E. There's only about 33,000 of them that have to migrate across, which is nothing by comparison. To give you a sense now, the diameter of one of these lipids is about 10 to the 10th squared, surface area. So we think about how many lipids would be on that surface. What fraction of that surface would be charged compared to the number of molecules. So clearly you're interested in that, so we'll stop there and move on. But the point is there's all kinds of applications to this. Not just on the large scale electronically, but even on a biological, biomedical scale, microscopically. Okay, so, second order of business. Energy associated with a charged capacitor. When you have a charged capacitor, you have a corresponding electric field, which is related to the potential difference between the signs. Well, in that electric field, you have potential energy. And that potential energy accumulates as work is performed to physically push charge onto those capacitors, or onto those capacitor plates, those conducting plates. So, when you charge a capacitor, it requires, if you will, work. And because it's an electrical phenomenon, the work required to charge a capacitor is related to minus the change in the electric energy associated with the capacitor as it's being charged, or as it was charged. So we start out, for instance, with a capacitor that has no charge, and we have a potential energy of 0. Then we charge it. Now we have a certain voltage across it, and we have a plus and a minus Q, and we have a certain potential energy. The work, electrical work required to physically force that charge onto the capacitor relates or is directly correlated to the change in the potential energy. Now, we've already learned a little something about potential energy. If we call this end 0, and we call this end plus V, and we look at the charge over on this side, Q, potential energy on the positive side with respect to the minus V side will be equal to the amount of charge that's on there times V. Potential energy is, or V is U over Q, right? Potential energy per unit charge. So this is the potential energy that's physically on this thing. So the change in potential energy is Q V as well, right? Because if you start from 0, then you increase to Q. Or I'm sorry, you increase from 0 charge, 0 voltage up to some potential energy. This quantity would be equal to minus the work associated with the electric field during this process. Why would this be a negative? But the electric field is not what's storing the charge, is not what's putting the charge on there. It's driven by something else, and the electric field is being produced, and therefore opposite, if you will, the direction of the accumulation. Because the field, or the charge doesn't go across this way, it comes from the outside. So it's a bit backwards. Now, so if we were to increase, we have a charged capacitor now. If we have a capacitor with a certain amount of charge, PQ, will produce a dV. So any increase in charge that we add on here will correspond to an increase of V plus dV, if you will. The change in the potential energy, if you will. As you add that additional amount of energy, will be directly related to the total charge, which does not increase by very much, relatively speaking, dV. And we can re-express Q in terms of the capacitance and the voltage that is not changing by very much, dV. So the amount of work, if you will, to add a tiny little extra addition of charge and the corresponding voltage increase will be related to functionally how this changes. And the change in the potential energy then will be related to evaluating this integral of C dV going from wherever the initial condition is, initial, to whatever it is after it's done charging. And what we're left with then is an expression that looks something like this. The amount of stored energy in a capacitor, which is opposite the work done by the electric field against pushing those charges there, is related to the difference between the square of the voltage, 1/2 the square of the voltages times the capacitance. Look at this very, very carefully. It tells us something about what this voltage is as that charge has been added. It's not the final voltage between here and here. It's half the voltage. So let's just note that when V initial is 0, then the energy, the change in potential energy to raise it to some voltage, which will be the potential energy stored, will be equal to 1/2 C V, if you will, final squared, whatever the voltage is. And as a note, this would happen to correspond to C times V divided by 2, which corresponds to Q times V divided by 2. This is Q times the average voltage as you go from 0 up to this value. In other words, the relationship between Q and V and the stored potential energy is related to the average V during the accumulation of Q. Because the more you add on, the more work is required. So early on, it takes less work to push charge onto the surface. And as time goes on, it takes more and more and more work to push additional charges because of their own electrostatic repulsion. So make note of this. It's a little bit deceptive, and that's why I wanted to sort of point it out. You get a point charge in space, the potential energy of that is just QV, whatever its voltage is there times Q. But when you think about the stored energy in a capacitor, it's, because you've got negative one side and positive on the other, it's kind of like starting at the center and pulling charge over to one side, not going all the way across. You've got negative on one side, positive on the other. It's kind of like, it's a sliding scale, so it's not quite so obvious. It's a good conceptual relationship to remember. But ultimately, every time you double the voltage, you quadruple the energy across a capacitor. So it's an energy storage device. There are certain advantages to high voltage